ladies and gentlemen.
So let's talk solid geometry. So solid geometry, also known as three-dimensional geometry, is a small topic in geometry taught in high school. Primarily, we'll be focusing on three different types of three-dimensional solids. We'll focus on prisms, we'll focus on pyramids, and we'll focus on spheres. So let's talk prisms first. So a prism is any three-dimensional shape whose top and bottom, that we'll call them bases, are congruent shapes. So they're completely congruent, same size, same shape, same angle, same everything. And they're connected with rectangles. So any shape that fits that definition would be considered a prism. So the volume of any prism is the base area, the area of said base, times the height. And the height is the perpendicular distance from base to base. So let's talk about some common types of prisms. Well, we have rectangular prisms. We have a prism where we have a rectangle as the base, and the area formula for a rectangle is length times width, which is why we can turn base times height, or base area times height, into L times W times H instead. So length times width times height. Most common prism you'll see. Cubes are special rectangular prisms where all of the side lengths are equal, also meaning that all the faces of the cube is a square. So the volume, instead of being base area times height, could be simplified into side lengths cubed, because the base area for a square is side length squared, times that by the height, which is also the same as the side length, and you get the side length cubed. Cylinders are special prisms that have a circle as a base, so their formula contains pi r squared h, which pi r squared is the base area of a circle times the height. So any prism you have, whether it be triangular, whether you have a hexagonal, doesn't matter. The area of the base times the height is the volume of said prism. The next type of solid is a pyramid. And a pyramid, the major difference between a prism and a pyramid is that a prism meets from congruent base to congruent base. A pyramid meets from a base to a singular point on top, which we call the apex. Sometimes we refer to it as a vertex, but that is a more universal term for a lot of different places. The apex is specifically the very, very top, the one opposite of the base. The formula is actually very similar to that of a prism. In fact, it is the volume of a prism divided by 3. So exactly the same way that you would find the volume of a prism, you just take that and divide that by 3. So we take the base area, times it by the height, and divide that by 3, or multiply it by a third, so you might see formulas show up in a lot of different ways that are essentially the same. So, common types of pyramids. We have rectangular pyramids, so instead of being a rectangle meet a rectangle, it's a rectangle meeting at a point. And that has a very similar formula to the rectangular prism, just divided by 3. Length times width times height. Again, this part here is your base area. So, generic to more specific. Cones. Cones are your special pyramids that have a circle as a base. So they get that fancy pi r squared that you get from the area formula for a circle. But again, any pyramid can be found base area times height divided by 3. So if you have any weird type of pyramid, if you have the base area, you can multiply it by the height, divide it by 3, and you find the volume. So not bad at all when it comes to those. So prisms, base area times height. Pyramids, base area times height divided by 3. So the last solid we're going to be talking about is the sphere. You can kind of think of a sphere as a three-dimensional circle. So a circle is defined as all points that are equidistant from a center, that distance being called the radius. For a sphere, it is taking that to the third dimension. So it's every point that is the same distance away from a point in three-dimensional space. And that distance is also called the radius. Its formula is unique. It is 4/3 pi r cubed. So, a little out there. You can actually prove this in calculus if you make it there. Very exciting to do. And in fact, it's an exercise I throw at my students all the time. But for now, you just have to memorize it. Sometimes it's given to you depending if what standardized test you're taking or what say you. But the formula again is 4/3 pi r cubed. So how I kind of think about it a little bit is it reminds me of, the top half anyway, reminds me of a pyramid that meets at a point. So that's where I get the divide by 3, because it kind of reminds me of a pyramid, but it's fatter than a pyramid. A pyramid is kind of consistent as it goes up, where a sphere is kind of fatter and works its way back in. So that's why it's twice as much, and then you double it again because you have the top and the bottom. If that doesn't work for you, no worries. But again, 4/3 pi r cubed, and that might help out a little bit with memorization. The next major idea we're going to talk about is surface area. The surface area of any three-dimensional shape can be found by basically unwrapping the shape into its two-dimensional pieces and then finding the area of each of those individual pieces and then adding all of them together. Some of them are easier than others. Some of them have formulas. Sometimes those formulas are given to you, but if they're not, just try to picture breaking that apart into all of its two-dimensional components. For example, a cube can be broken up into 6 individual squares, all with an area of the side length squared. So the surface area of a cube is 6 times the side length squared, because, again, we get 6 squares from breaking apart a cube. So there you have it. Some of them are a little bit weird and have really special formulas, especially when you get to like a cone, for example. It's going to have an interesting formula. But typically, they'll either give it to you or you'll be able to easily figure it out. The last thing we're going to talk about is kind of known as Cavalieri's principle. Basically, in a nutshell, it doesn't matter if I give you a three-dimensional solid that is tilted in any way, as long as when I slice the three-dimensional figure, that slice, the area of that slice, is the same as it would be normally, then the volumes are going to be exactly the same. So if I take a cylinder here, and I take a cylinder that has all of the same dimensions, and I tilt it some, but the perpendicular height from base to base, meaning we make a 90-degree angle with this base, a 90-degree angle with this base, is exactly the same, radius is the same, it doesn't matter that it's tilted, the volume formula will be exactly the same. What makes this a little bit different is sometimes you'll be given the slant height, and that you'll have to use like Pythagorean's theorem, for example, to find what the actual height would be, or maybe some trig that you'll learn about a little later. But if you have all the same dimensions, just one's tilted, same volume. So let's try out a problem. The volume of a cube is 27 cubic inches. What is its surface area? Well, the volume of a cube is side length cubed, and we said that the volume is 27 cubic inches, so the side length cubed is equal to 27, which means we need to do the cube root. One number times itself is 27. That would be 3, because 3 times 3 is 9, and that times 3 is 27. So that is the side length. So each side length is 3 inches. Surface area, the surface area for a cube is 6 times the side length squared. So we're going to plug in that 3. So 3 squared times 6. 3 squared is 9. So it'd be 54 square inches. So cubic inches or cubic units are used for volume. Square units are used for area. And then no quantifier is really needed for a singular dimensional unit. Next up, we have the volume of a rectangular prism is 168 cubic inches. If the length is 6 inches and the width is 4 inches, what is the height? So we have a volume, we have a length, and we have a width. Well, the volume of a prism is equal to length times width times height, and we are given all but one piece of information. We're given the volume is 168, we're given that the length is 6, we're given that the width is 4. We can find the height by solving. So first I see that we can do 6 times 4, and that would be 24 times h, and that equals 168. Now we can get the h alone by dividing. So we can divide this by 24, divide this by 24, and I don't know what that is off the top of my head. So how can I make this nicer for myself? Well, I know that 168 should be divisible by 4. I know that 100 divided by 4 is 25. I know that 60 divided by 4 is 15, and I know 8 divided by 4 is 2. If I add all of those together, I get 42, and that 42 is reducing the numerator by 4, by a factor of 4, so we're going to reduce the denominator by a factor of 4 as well, leaving us with 42 over 6. And 42 over 6 is very easy to see that this would be 7 inches as an answer. So not that bad. Last but not least, if a cone has a volume of 75 pi cubic centimeters and a height of 9 centimeters, what is its radius? So the volume for a cone, volume of a cone, is equal to pi times r squared times h, because pi r squared is a circle, times h divided by 3. And now we can substitute in all that we know. We know that the volume is 75 pi. We have a pi. We have r squared. H is 9, and we're dividing this by 3. Well, 9 divided by 3 is 3, so we can already simplify that out, leaving us with 75 pi is equal to 3 pi times r squared. Let's divide both sides by 3 pi. And in doing so, pi divided by pi cancels. 75 divided by 3 is 25. So we are left with 25 is equal to r squared. Taking the square root of both sides, we can see that r is equal to 5, and the unit would be centimeters. So that is it. There's a lot to do with solid geometry, and we kind of condensed that as much as we could. So if you have any questions, please let me know. Practice will make perfect with this. Good luck to you, and I hope to see you in the next video.